I'm hoping you noticed that plugging in a number and evaluating a limit as x approaches a number is only different if the graph is exhibiting some sort of strange behavior at that number. Like for instance, if it has a hole in it, or an asymptote, or it's some sort of step function where the graph is jumping from one point to another. If a function is behaving normally at a given point, plugging in a number and evaluating the limit as x approaches a number is the same thing. Let's take a look at the function 2x plus 1 on the graphing calculator. It's just a line. At x equals 3, well, when x equals 3, the graph is not exhibiting any strange behavior. Evaluating the limit as x approaches 3 is as simple as tracing 3 or just evaluating the function at 3. If I plug in 3, 2 times 3 is 6, and 6 plus 1 equals 7. Let's take a look at this function and see if it's exhibiting any strange behavior where x equals 1. I have it typed in. Let's look at its graph. This function appears to be behaving normally everywhere. It just appears to be a parabola. I don't see any strange behavior where x equals 1. Let me try plugging in 1 and see what I get. So I'll trace 1, but interesting, I don't get an output when x equals 1. You can't really tell from the graphing calculator, but this function appears to have a hole at x equals 1. Watch, if you plug 1 in, 1 minus 1 is 0. We're dividing by 0, so f of 1 would be undefined. This function, however, will have a limit as x approaches 1, because as we approach 1 from the left-hand side, we seem to be headed towards this point, and as we approach 1 from the right-hand side, we seem to be headed towards the same point. We need to figure out what this point is. Of course, tracing 1 doesn't help us because the graph is undefined at 1. So what we need to do is look just a hair to the left of 1 and a hair to the right of 1. I'm going to trace a number that's just a hair to the left of 1. I'm going to trace 0.99999. When I trace 0.99999, I get 1.99999, which is essentially 2. Now let me trace a number just a hair to the right of 1. Let me trace 1.00001. When I trace 1.00001, I get 2.00001, which is also essentially 2. It appears to me that this point where the hole is at the point 1, 2. So the limit as x approaches 1 equals 2. I'm going to use the same function for both examples 3 and 4. Let me type this function in the graphing calculator. I put my numerator of x minus 2 in parentheses. I put my denominator of x squared plus 3x minus 10 in parentheses as well. Let's first find the limit as x approaches negative 5, and I can see that there's certainly some strange behavior at negative 5. This graph has an asymptote where x equals negative 5. If I trace negative 5, the graph is undefined. As I approach negative 5 from the left side, my graph is going down to negative infinity. As I approach negative 5 from the right side, my graph is going up to positive infinity. Let me trace a hair to the left of negative 5. Let me trace negative 5.0001. At negative 5.0001, I get a very large negative output, negative 10,000. Let me trace a hair to the right of negative 5. Let me trace negative 4.9999. At negative 4.9999, I get a very large positive output, positive 10,000. In this example, I got essentially the same output when I was a hair to the left and a hair to the right. When I was a hair to the left, I essentially got 2. And when I was a hair to the right, I essentially got 2. The limit was 2. In this one, when I'm a hair to the left, I'm getting a negative output. When I'm a hair to the right, I'm getting a positive output. These numbers are not the same numbers. I'm going to say that this limit does not exist. Let's go see what happens with that function if we try to evaluate the limit as x approaches 2. Let's first see what's going on at 2. If I trace 2, the graph is undefined. This graph must have a little hole in it when x equals 2. So let me look just a hair to the left of 2. Let me trace 1.9999. At 1.9999, I get an output of positive 0.14285,918. Let me now look just a hair to the right of 2. Let me trace 2.0001. Now, these numbers aren't exactly the same, but they are pretty close. They're both 0.14285. I'm going to say this limit is approximately 0.142857. This output was a little bit bigger than 0.142857, and this output was a little bit smaller than 0.142857. Or I suppose we could just say that this limit is approximately 0.14285. We can evaluate limits numerically by looking a hair to the left and a hair to the right of where we're trying to evaluate the limit. A hair to the left of 0 would be negative 0.0001, and a hair to the right of 0 would be positive 0.0001. It's not an exact science how many zeros you use. I suppose you could first try plugging in this number, but notice in our denominator, 0 plus 1 is 1, the square root of 1 is 1, and 1 minus 1 is 0. This is going to be undefined at 0. That's why we're going to look a hair to the left of 0 and a hair to the right of 0. Let me type this function in my graphing calculator. And let's take a look at the graph. Of course, if I trace 0, we already know that it's going to be undefined. So let's go a hair to the left, negative 0.0001. I get 1.99999, or essentially 2. And let's look at positive 0.0001. They're not exactly the same. This is a hair less than 2, this is a hair more than 2, so I'm going to imagine that if there was not a hole in the graph, it would go through the point 0, 2. This graph has a little hole in it at 0, 2. In example 6, we have what we call a piecewise function. This function has two pieces. It's 1/2 x plus 3 when x is less than 4, and then it's x minus 3 when x is greater than or equal to 4. Let me remind you how to type a piecewise function into your graphing calculator. I'm going to type the whole thing in as one function. I'm going to graph 1/2 x plus 3 when x is less than 4, and then I'll also graph x minus 3 when x is greater than or equal to 4, but please notice that this is all one function. So y equals, I'll open up my parentheses, 0.5x plus 3, parentheses x, and second math will allow me to access my inequality symbols, less than 4. Then plus my other piece, so in parentheses x minus 3, and also in parentheses x is greater than or equal to, second math allows me to access my greater than or equal to symbol. This graph certainly seems to be exhibiting some strange behavior where x is 4. When we get to 4, the function is jumping from here to here. If I want to evaluate the limit as x approaches 4, I need to look a hair to the left of 4 and a hair to the right of 4. A hair to the left of 4 would be 3.999, and a hair to the right of 4 would be 4.001. Let me trace 3.999, and let me trace 4.001. These numbers are not matching, so I'm going to say that this limit does not exist. As we approach 4 from the left side, we appear to be headed towards the point 4, 5. As we approach 4 from the right side, we appear to be headed towards the point 4, 1. We're not headed to the same point from both directions. Let me just change one thing about this function. Let me change the x minus 3 to a 9 minus x. I'll go to my y equals, and I'll change this x minus 3 to 9 minus x. Now as we approach 4, both sides appear to be headed towards the same point. We need to determine what this point is. To find the limit as x approaches 4, I'll look a hair to the left of 4 and a hair to the right of 4. Let me trace 3.999, and let me trace 4.001. They're both less than 5, but it seems that we're headed towards the point 4, 5. I'll say the limit as x approaches 4 equals 5. All right, hope that helps with evaluating limits.